In this video, let's just go into a little more detail with Boolean expressions. There's something that I didn't talk about in the Boolean expressions video that I think is important and that we should talk about when it comes to programming languages and the way that Boolean expressions are evaluated. Now, we're going to take a closer look at specifically AND and OR. We mentioned that C++ supports NOT by default, and we did XOR with that little plus in the circle as an example in the Boolean expressions video. Just as a refresher, AND is only true when both things that it's operating are true. Here I've taken this from, I believe, a math or a computer engineering point of view. So here they're not using the double ampersand and the double stovepipe for AND and OR respectively. They're just writing them next to each other and doing plus, but these do still mean AND and OR. And the other thing they've done is they have written 0 to be false and 1 to be true, which is okay. As we saw in the Boolean expression video, that's how C++ prints it too, so that's probably alright for us to understand. And what we were saying was, AND is only true when both of the things that you're ANDing together are true. So if I have X and Y, it's only true if X is true and Y is true. If X is false and Y is false, it's false, or if either one of them is false, then it's false. On the other hand, OR is only false if both parts are false. So it's almost like an opposite to AND. OR is true as long as one or the other is true. If I'm taking X or Y, if X is true, then my result is true. If Y is true, my result is true. And if they're both true, then my result is true as well, right, is what that table says. So now that we've refreshed on that, we can consider the fact that 3 out of 4 cases AND is false, and 3 out of 4 cases OR is true. Now that's important because it doesn't have an even distribution of true and false. If that was the case, then we would expect 50 to be true and 50 to be false. 50%, that is. But that's not the case, right? So what the compiler will do is it will only evaluate expressions that are not already specifically true or specifically false depending on the scenario. And I said compiler, I mean runtime environment, which is what we run it in rather than the compiler itself. And what I mean by this is, let's just say I have A and B and C and D, and we'll just stop it at that. If A, B, C, and D are some kind of Boolean expression that have truth values, so they can be either true or false, we know that AND is only true if everything is true. And normally it's a binary operator, right? We only do it on 2 things. But if we consider it here, even though I have 4 things ANDed together, all 4 of these things have to be true in order for this AND expression to be true. A has to be true, and B has to be true, and C has to be true, and D has to be true in order for this to be true. And so what the runtime environment will do is it will evaluate these left to right, and if it knows that it's not going to be true, it will stop evaluating. So for instance, if I had A was false, then it doesn't actually matter what the rest of this is. So we have B, C, D here. And the reason that's important is because if A is false, then we know that this can't be true anymore, because the only way that it's true is if all 4 of these parts are true. Which, if you think about it, if you know a little bit of math here, then knowing these are in binary, if only one possible outcome gives us a true outcome, and there are 4 variables, each with 2 possible values that they can take on, and that's 2 to the 4th possible ways that we could assign to this. There is 16 possible ways this expression could go, and only 1 out of 16 of them would ever be false. So if we have one of those other 15 cases, then it would be in our best interest to stop evaluating this early and not waste the computation time doing B, C, and D. And knowing the fact that this is false, if a single part is false, then it will stop doing that check. So here in the example I've given, A is false, and something to consider is that because of order of operations, right, if all of the operations are the same, they always give you that rule, you should evaluate left to right, and that's the way that it will evaluate it in any case. So if it goes from left to right and encounters one single expression is false, it will stop evaluating and it will just say, okay, this whole expression is false. So here, if A is false, then all of this just gets thrown out and it says, okay, well, it's ANDed together, that's my major operator, it is false. So this equals false. And so the name for this that it does is it is short circuit evaluation. Let me move this up a little bit. It's called short circuit evaluation, and it's called that because it will stop short of evaluating the whole thing if you ever encounter a single false. And so this is done for computation reasons, because if you have like 20 of these expressions that are all ANDed together, then it's in your best interest to stop as early as possible because you don't want to evaluate all the other stuff. And this more so becomes apparent when we do things that are expensive. And by that I mean computationally expensive, in that they take more time to run in the CPU than other sorts of operations. So an example of this would be if I had the expression, let's just say my code is int x equals 4, and then I have a check here, let's just say it does an if check, and it says if x is greater than 7 and sine of x is, let's just say, less than 10, something like that, then we know that this first part, so the way this will evaluate is we have two expressions, right, that are ANDed together. We have this part, and then we have this part with the sign x less than 10. So this would be like the A above, and this would be the B above. It is going to evaluate these expressions left to right, which means it's going to start with this one, and it's going to do this one with the sign of x first. Well, this one is going to fail, right? This is a false, because 4 is not greater than 7, so this is going to fail, which means that this isn't going to get run. And why that's important is because x greater than 7 is a very easy computation. Just checking two numbers, specifically integers against each other, is pretty easy. It's relatively fast. The other one is both checking numbers, and it is also taking sine. And sine, if you have taken a calculus course, you probably know it can be written as a Taylor series, and that is the way that the computer generally is going to calculate trig functions. So that's going to take some amount of time. They do it to some term. It's not infinite like the actual Taylor series is, but it's going to have to do a lot of computations in order to take sine of x. If you're not familiar with the Taylor series, basically it has to do a bunch of additions. We'll just leave it at that. And so this is very expensive. This is expensive. It takes a lot of time to run. And so, as a programmer, knowing that this does short circuit evaluation, you should consider putting things that are less computationally expensive first in your evaluation. That way, if worse comes to worse, you save the expensive ones for later, so that it won't run the ones that take a long time most of the time, at least if anything fails in an AND statement like this one. And AND has this, OR does as well. We'll have to scroll back up here for a moment. Whereas AND was only true 1 out of the 4 cases, it was only true when both parts were true, which meant that it's false most of the time, so we'll stop evaluating early if it's false. We can do the same thing with OR, because OR is true unless both parts are false. Here, let's just scroll over a little bit. So if I had A or B or C or D, what this means is that only one part has to be true. Whereas the other one, it was only one part had to be false for the whole thing to be false. This one is only one part has to be true if the whole thing is true. So if I had A equals false and B equals true, and let's just say C equals false and D equals false, then because I'm asking an OR, which is one part or more has to be true, then this whole expression is true even though only B is the one that's true. So here I would have A is false and then B is true. So as far as the evaluation goes, it would do A and then it would do B, and then C and D get ignored. because once it hits a single true going left to right, it will just not evaluate the rest. And again, we can do this to kind of shortcut some things and attempt to not evaluate more expensive operations that we would have to evaluate in the future. And again, this is just called short circuit evaluation. It's the same for both AND and OR. So something to be aware of, you want to make sure that you know that short circuit evaluation is there because you can both save time, and you also might get some weird side effects if you, for some reason, and it's very common, to put something that executes code, which we'll get to in a later video how you would do that, and it doesn't get evaluated because the short circuit evaluation happens. So you may want code to be executed, but if it gets short circuit evaluated, it might not get executed. Again, if we go back to the example that I did earlier, you might have something in place of sign. We've included CMath in the past, and it is something that somebody else has written, so they've written this code before, but you might write your own code that you call in a similar way to the sign function, and it might need to do something important, maybe print something, or do something with the system, or write to a global variable, or a class member, or something like that. And if it short circuit evaluates, then your code is not going to get run. And again, we'll get to that when we get to functions and very much later structs, examples of when that might happen. Anyways, that was just a quick overview of short circuit evaluation. Wanted to make sure that we cover this because I forgot to talk about it in the Boolean expression video.